Recording in progress. Good evening, everyone. I think we will be starting in a few minutes. We'll just wait for others to come. But in the meantime, please, if your mic is on, please take it off. Mopalana, Pala, the voice is coming through. Please ensure that your mic is switched off. Good afternoon, everyone. We are ready to start. Once again, I have pleasure in welcoming all of you to this session, which is the 7th session we are conducting with the learners from grades 7 and 8 up to grade 9 to train you for the high-flying competitions. South African Maths Foundation competition called the Maths Olympiad, and the training is at a high level. We want to train you so that you can eventually get into round 3, which is the final and the last round, the last 100 of 5,500 students or more, no, more than that, who actually participate. Okay, so the problems are quite challenging, and you learn a lot from this. I think by now you would have realized that there are many things that are interesting in mathematics, but if you don't know how to do it, then it becomes a problem to solve it. So you have to think about building up a strategy to solve problems. Often the best strategy is to use symbols for unknowns and create equations. Once you got enough equations, then you can solve the equations. That's one of the prime strategies. But like that, there are many other strategies which you can only pick up when you do enough problems. So we are selecting some problems from session 7 in the book called Problem Book. If you go to that problem book under juniors, which is the first half of the book, and go to session 7, you will see that these problems are from there. But there are many other problems in session 7 and the other ones as well, which we don't do because we don't have the time to discuss all of them. I simply selected some problems from that problem book and we are tackling them. But if you have any issues with those problems and you have difficulty in solving them, you can always write to your coordinator or you can write to me and I will be only too happy to help you along solve those problems. All right, so with those few remarks, let me go straight to oh yes, I also want to congratulate the junior teams. I don't know how many of you actually uh, participated in the team competition, um, but if you did, uh, you have done exceedingly well. Our teams, the teams which consist of people who have been attending these classes, um, they came second in the whole country, second and third, out of 42 teams which participated. So I want to compliment you guys. I am deeply encouraged by that and hope to continue these classes so that you become experts in problem solving by the time we finish all. All right, so that now brings me to the first question. All right, the first question says, Kevin received a 100 Rand gift voucher to be spent at a store. He aims to purchase uh, sorry, my screen is blocked by something. He aims to purchase 20 items using all the money. The items he's interested in are pens, notebooks, and rubbers, and they give you the price of each one of those items. Pens, notebooks, and rubbers. List in the form, and we have in brackets, pens, notebooks, rubbers, all the different ways he can spend all his money if he buys at least one of each of the three items. So let's just try to unpack what this problem is. You've got 100 Rand to spend, and you're going to buy three items, and we're going to call them okay, we're going to call them P, N, and R. P, N, and R. These stand for pens, notebooks, and rubbers. We can call them X, Y, and Z or any other thing, but if you've got symbols like this, then you know exactly what you're talking about. P, X and Y and Z, they don't really give you any information. So we can use these symbols, which are much more friendly. So he's got the pens cost. Okay, he needs to purchase 20 items. So altogether, the number of items are P plus N plus R. Right? Those are the total number of items that he will purchase, and that's 20. Okay, I don't know why I've used red. Then I've gone back to my black. And he also has got 100 rands to spend. And we know what each one costs. Pens cost 5. For each pen, it's 5 rands. So he's buying P pens. So the cost of the pens is 5p. And likewise, the notebooks cost 7 rands each. The N notebooks, so the total cost of the notebooks is 7N, and the same with the rubbers. And altogether, this total cost is there. And they say here that he spent all his money. He says that's useful, right? So the total amount that he spent is 100 rands. If he didn't, then we'll have to say it's less than 100. You would have had some change. Okay, but now he spent all his money, and that's the only information that you're given. And you're asked to find all the possible values for P, N, and R. They are all positive numbers, remember? P represents numbers. So P, they also say he buys at least one of each of the three items. So P is at least one. And the same thing with N and R. They all are at least one. Okay, now, so how do we solve this? We've got two equations in three unknowns. And a very important thing is that all these numbers are natural numbers. The way to write this is like this: P and R are elements. N is the symbol here is equal to the set of natural numbers. That's the symbol that is usually used for a natural number. Integers we use Z, and reals are. Put a double stroke in each of those cases, right, to distinguish them from the normal N. So these are counting numbers. You can't have by 3.5 or square root of N rulers. All right, now how do we solve this? We have to eliminate. Now you can, the way to eliminate is to multiply the top, multiply one of them so that you get the same number at the bottom. Like for instance, if I multiply the top by 7, then I'll have 7n. Yeah, and then what we will do is subtract, and those n's will disappear. So that reduces the number of unknowns. See? So you try to get the coefficients to be the same. All right, now in this case here, it's not difficult to get the coefficient to be the same. You simply have to multiply by something. But how did you notice also, you got this is 20 and this is 100. So 520 is 100. So it'll be nice to eliminate or to multiply by 5. Right? You can, that way you'll eliminate the p's as well. So what I'm going to do is multiply everything here by 5. You can't just multiply one of them. You multiply the left-hand side by 5 and also the right-hand side by 5. And that will not change the equation. It's the same equation, right? Now, why did I do this? This way I can eliminate, so I can subtract. I'm not going to write it down. I'm going to subtract this minus this. That's 0. 7 minus 5, 7n minus 5n. 2r minus 5r is minus 3r. 100 minus 100 is a 0. So you've got one equation with two unknowns. It's very nice because you've got 2n equals 3r. Right? I can bring to the other side. So if you multiply the number of rubbers by 3, you'll get twice the number of notebooks that he buys. So that's it, interpretation of it. But the other very important thing is that 2n means that this number here is even. When you multiply a natural number by 2, you're going to get an even number. So the thing about this is the 3r is even, because it's equal to twice a natural number. But 3 times r being even means that r is even. The only way, 3 is odd, you see. So to get 3r to be even, now this is very useful. That means r cannot be 1 or 3 or anything like that. Okay. Okay, now let's try to substitute this in the first case in this. So I've got p plus n plus r is 20. I don't like fractions. So let me put 2n, multiply right through by 2. And then in place of the 2n, I can put 3r. because 2n is equal to 3r, you see. So now I have one equation with this is 2p plus 5r is equal to 20, and 2p is equal to 20 minus 5r, which is 5 into 4 minus r. Now I'm bringing the r to the other side. See, it's always nice to get something in terms of the other. Like here, you got 2n in terms of 3r. So n is in terms of r, which means I can, whenever I see n, I can destroy it. And then that kills an unknown. It reduces the number of unknowns. So, like here, that is what I did. Yeah, I put the 2p on this side because I can see 5 goes into 20 and 5r, and then I can do this. Now, look, this is positive. It's actually positive, strictly positive, because p is bigger than 1. Right? And they're all natural numbers. So for 5 times something to be positive, so what can r be? R can be only it starts from 1, so r could be 1. Yes, r 4 minus 1 is positive, 5 times that, and r could be 2, r could be 3. But the moment you come to 4, it's 0, and 5 is negative. So the only possible values for r are 1, 2, and 3. So that restricts it quite strongly. But we also know that r is even, you see. So now that means r must be 2. Because the whole simple logic. See? First we decided that r is even, now we decided that r is actually equal to 2. So once we got r, then we can calculate everything else, because r is equal to 2. I can put r inside here. Let me keep put r equals 2 and put a bracket around that, or cage it. And if I put r equals 2 here, I have 2p equals 10. R equals 2, 4 minus 2, 5 times 2 is 10. P is equal to 5. Now you got P and R, so you can work out the others. So you've got 2 plus 5 is 7, and N is equal to 13. Okay, somehow I don't seem to remember this answer. So you got N is equal to 13. So that tells you what he bought. So the total number of books is obviously now, when you add them, you get 20. And the rubbers cost 5 rands each. So this one here is 25. And the N costs 7 rands. Well, you know what happened? I should have had 40 here, but sorry. I multiplied right throughout by 2. I should have multiplied the right-hand side by 2 as well. So that should have been 40. I'm sorry about this. And then in that case, I would have had 8 minus r. And then the values for r could be anything from 1 to 7. And then, but the r is even. So you have 2, 4, and 6. So there are 3 values for r. There are 3 values for r. And then, like what I did earlier on, you can substitute and get the different values for p. So I'm sorry about this. So when r is 2, it's quite right that n is then 3. Or n is 3. Okay, you can figure it out. Get these three values for r. R equals 2, 4, 6. And then substitute in all these equations. This is, here I've got n in terms of r. And then here I have p in terms of r. So once you got a value for r, then you can calculate n and you can calculate p. So that way you got all three. There are three different possibilities. So you have to go, one of the possibilities is this thing, 2, 3, no. N is 3, yeah, and Rabbis is 15. So this is one of the possibilities, but there are two others. Okay, now that took a long time to work out, but I hope you got the gist of it. The idea is to write down the equations, and remember that these are not any numbers, they are counting numbers, and that we exploit. We'll do that all the time. The accounting numbers you can exploit. You can talk about division and even numbers and so on, remainders with counting numbers. But with other numbers, you can't do that. So that's why the counting numbers helps you a great deal. All right, so let's get on to the next one. Find the value of k plus L if k and L are positive integers. Here again you've got the k. Sorry, my mouse battery is gone dead. All right, so you got k and L are positive integers, so you got k is greater, positive integers mean k is greater or equal to 1, and the same thing with L. And you got k plus L plus KL equals 54. Now, you see, it's very hard to actually work out what K and L are because you've got three numbers which when added gives you 54. There are many, many ways in which you can get three numbers added to give you 54, but you want that last number to be the product of the first two. See? You can try, you can use trial and error, but it might take you a long time to do it. So you have to figure out some way in which you can use mathematics to solve this. You see, if I have a product here, then it's fine, because then I can say I know what the factors are. See, I don't have a product here. Now, can we make a product here? Well, let's just investigate this thing here. K plus L plus KL. We can put K plus, and we can take out the L. L into 1 plus K equals 54. All right. So I can take out the L here. Then it strikes me that 1 plus K is a factor here. But if I can get a 1 plus K here, I can do that by adding 1 to that side. Then I'll get 55 on the side. So let me add 1 to that side. I'll get 55. And now you got 1 plus K is a common factor. Right? See, if you have AB plus AC, A is a common factor. A times B plus A times C. And you can take A out, and it's the same as A into B plus C. Very important factorization. Right? As long as you got same thing times something else, same thing times something else, you can take it out. So this 1 plus K is occurring in both cases. It goes into this 1 time. Right? It's not there, but 1 plus K times 1 is there. And it goes into this L times. So now you got a common factor, and you got a product now, which is very much better, because then you can say you can say what 1 plus k is. It's a factor of this, you see. These are all counting numbers. Right? So now we can have product of two counting numbers equal to 55, and we can mean that each one is a factor of this. So what are the factors? Factors of 55 are 1, 5, 11, and 55. You can check it out. There are only 4 factors. It's 5 times 11. Right. Now you can work out the different values for k. 1 plus k equals 1 means k equals 0. 1 plus k equals 5 means k equals 4. 1 plus k equals 11, k equals 10. 1 plus k equals 55, k equals 54. Right? So each of these is a factor. So once you've got that, then you can say what L is. Now, when k is equal to 0, now you can substitute here, you see. This is the key one. If k equals 0, we can do this mentally. This is 1, and then 1 times 1 plus L is 1 plus L. And here you get L is equal to 54. Right? And if k is equal to 4, you can try it out. This is going to be 10. You're going to get a 4 here, and you're going to get a 0 here. I substitute the different values for k into this equation here, and then you'll have one equation with one unknown, and you can solve them. You can do that. But it says here that k and L are positive integers. So you'll have to rule this one out. You have to rule this one out as well. If you rule this out, that is also ruled out. And that is also ruled out. So there are only 2 possibilities. K is equal to 4. You can put K, comma L. This is a nice way to write it down. And put round brackets. Is 4 and 10, or 10 and 4. K equals 10, and L is equal to 4. Right? There are 2 possibilities. But your question is find K plus L. But in both cases, K plus L is 14. So although there are 2 solutions, there's only one possible value for K plus L. That's the question. The question was not asked to find what K and L are. Okay, so that's the answer. So the trick here was to analyze this thing, and I've taken out this L as a common factor here. And then I say, I would like to factorize this thing. Right? If I got it as a product, then I'm very, very close to my answer. But as it stands here now, it's very difficult to work it out because there are so many ways in which you can add 3 numbers to get 54. So, and you can try that one, but it'll take a long, long time to eventually get to the answer. But when you write it as a product, then it's a different ball game altogether. Okay, so let's get on to the next question. So here you say, let A, B, and C. Again, it's a very similar problem. You're solving an equation with whose unknowns are positive integers. But here, this equation is a little bit more complicated. You may wonder where this thing came from. Why all these funny numbers? Then if you look at it carefully, you'll see that 365 is the number of days in the year, and this is the number of months. You got 31. You can see a solution straight away here, because this is, there are some months which have got 31 days, there are some months which have got 30 days, and there's one month which may have 28 days. So immediately we can see A equals 1, and you have to count how many days there are which have A equals 1, only 1, and you have 30 days of September, April, June, and November, so there are 4. So B is equal to 4. All the rest of 31 So we are already taken care of 5. So C is equal to 7. Right, but you're not supposed to do you can do it like that by inspection, and that is where you just don't jump into solving the problem, but you recognize it and say, hey, I think I know the solution. I can see what they are trying to get to. They're counting the number of days in the year, right? And for each month now, they're counting how many days there are in the month, and then altogether that way you can get to 365. Okay, but now suppose we didn't recognize that. How do you solve this problem? Can we get 1, 4, and 7? All right, now the first thing we do is notice that 31, you see, you've got 31C, that's a large number. So the left-hand side, now don't worry about months and all that. Now these are total unknowns, they're algebraic symbols. So the left-hand side is certainly positive. See, okay, what we can do is we can say 31C. Let's talk about 31C. Now, all A and B are all positive integers, so actually it's strictly less. A is greater than 1, B is greater than 1. So this number here, the 3 numbers are added together. So 31C will certainly be smaller than the sum of all 3, which we know to be exactly 365. So that tells you that 31C is less than 365. And that gives you some possibilities for C. The highest value for C, so C is less than 365 over 31. And when you try this thing, I think you get 11 and 24 over 31. Something you write as a mixed fraction. Right. And, but C is less than this, and it's a positive integer, so it goes up to 11. Right? Only 11 is the highest value you can have for C. You can't have 12. 12 is not less than this. So there are 11 possibilities for C. All right. Now, what else do you know? If you look at this thing, you can see that this is even. This is even because you're multiplying by even number. And this is odd. So maybe we can say something about this. Now you got these two add up to an even number because 28 times any number is even. Right? When you take an even number multiplied by anything you like, it's going to be even. So you got sum of 2 even numbers. So this part here is even. No, 31C is odd. Why? Because even plus what will give you odd? This one here can't be even because even plus even will be even. But what's the argument that we use here? They're all logical arguments, right? All common sense. So 31C can't be even because otherwise you'll have the left-hand side is even and the right-hand side is odd. So, but if 31C is odd, then C is odd. 31 times number is odd means that number must be odd. Any number, an even number times anything is even. So now C is an odd number from this lot. So you got 1, 3, 5, 7, 9, and 11. So there are 6 possibilities for C, right? So we're sort of zoning in. And I don't think I can say anything more. I've taken 31 because that will make C as small as possible. I want to make. All right, so now where do we go from here? Now this means that we can write down, substitute all these values, and you have 28 plus 30b is equal to, now there are various possibilities, because it's actually equal to 365.28. I'm going to bring A and B on one side because I've got possibilities for C. So I can bring it to the other side. Okay. So now when C is equal to 1, you got 365 minus 31 is 334. If C is equal to 3, you have 365 minus 93 is equal to 272. And if C is equal to 5, then you got 31 times 5 is 155, and 365 minus 155 is 110. See, I'm working it out all this mentally, but you guys, you'll also have to do it by pen and paper because you're not allowed a calculator. Okay, and finally, when C is equal to 11, you got 341, you got 24. Right. Okay, this is 28A. Now, you can immediately eliminate 24 because this thing is bigger than 28A. See, so this number here is larger than 28 because B and so larger than 28. Larger, greater or equal to 28. So this is not possible. Why? Because 28A plus 30B is greater or equal to 28. Why do we say it's greater or equal to 28? Because all of them are positive here, you see. So 28A plus 30B certainly is bigger than 28A. Actually, I can put greater than 28A, and A is greater or equal to 1. So therefore, they say positive integers, see? So all of them are greater or equal to 1. So therefore, 28A will be bigger than 28. So this thing can't be 24. So we can eliminate this 24. So we have 3 possibilities. And we can, all of them are even. So you can divide by 2. And you get 167, 136, and 55. Okay, so now you have to, we've got one equation with 2 unknowns, and we know that A and B are positive integers. And at this stage here, we just have to try to calculate because I've got 14A now is equal to any one of these minus 15B, right? 167. 14A, if I make 14A the subject, then this, now I can try the various values for B. I can put B equal to 1, and then I get 156. 14A can't be 156 because it's a multiple of 14, right? So like that, you can try this thing out, and I'm trying to see whether I can work this thing out mentally, but for some reason I'm not getting an answer. Um, okay, I think I made some kind of a wrong calculation. But what happens here is that only one of these actually works. I must apologize again. Made some kind of a wrong calculation. Okay, because if you put B equal to 1, then you get 167 minus 15, which is 152. That's not a multiple of this. Oh, I see. Then you can try b equal to 3. You get 45. 122, b equals to 5. So you have to try all different possibilities. Okay, I can't see the solution straight away, but so you try the various values for b, and you have to get a to be a positive integer. All right, so you can try this thing out with a strategy. All right, now the next problem. Just give me some time. It's not right for me to just stop like that. I should know where I went off. C is odd. So C is odd. There's some calculation I made which is not right. This is supposed to be 210. Yeah, this is 210. And that ought to give me, so this is supposed to be 105. And B equals 7 and A equals. Yeah, anyway, I can't see it, but this is 365 minus what was that? 210. 365 minus 210 is 150. Anyway, this is there's some mess up with the calculation, but you'll get there. All right. Unfortunately, I can't remember what the solution is, so I can't tell you what it is. But you got the idea how to solve that problem. That is the main thing. So we got enough problems like this with numbers so far, equations, how to solve, and you see several possibilities and try various things, make some deductions if some things are even or whatever, and try to use those kinds of logics to print down your values, and then finally you'll have a couple of values, try each one of them and write down all the solutions. That is the general way of doing this. Okay, now number 6, Pete writes down a 5-digit number. Then he deletes one of the digits to form a 4-digit number. Okay, let's see, what is he doing? He writes down a 5-digit number, maybe 36218, right? And then he deletes one of the digits to form a 4-digit number. So suppose I delete 2, then I get 3618. Right? And then he says if the sum of the original 5-digit number and the new 4-digit number, so when you add these, that sum is 52713. Okay, now we got this number answer here. But that sum is 52713. Now you're asked to calculate what the original number is. And so all you know is the sum of these quantities. Okay. So we have no idea what the 5-digit number is. So we've got 5 unknowns. I'm going to call it A, B, C, D, E. Right? Now this is not products. It's just this 5-digit number. Right? Okay, maybe I can just put equals to show that A is 3 here, B is 6, and so on. Now, when you eliminate, when you take out one of these numbers, your final answer is 52713. Now here's a Nice thing. What must you eliminate? What must you knock off? See, if you knock off A, you're going to get B, C, D, E. And E plus E is even, but this is odd. You see? So that immediately gives you an idea that if you knock off A or B or C or D, as long as E is alive, you've got a problem, right? As long as E is alive, then the sum of your original and that is an even number. And here we are told that it's this. So therefore, E is knocked off. So what you really have is that. This A, B, C, D, E plus A, B, C, D is that. Now, let's give a name to this four-digit number A, B, C, D. Usually for natural numbers, I use small n, be this four-digit number. Right? So what have we got here? We got n here at the bottom. And here at the top, you've got this four-digit number, A, B, C, D. I can put a 0 here, and I can put an E here. I can add these. And that will give you A, B, C, D, E. Right? So in other words, the top number is 10 times n. This plus E. So there's your n. You have to multiply this by 10 and add E to get this. So you got 10n plus E is equal to this quantity, but that is 11n plus E. Right? So 11n plus E is equal to 5,000 or 52,713. Now we recognize this thing here. This E is a single digit. It's a digit. So you recognize this one here because it's a multiple of 11 plus a number which is smaller than 11. So this is actually division. When you divide 52713 by 11, it's some multiple of 11 plus E. So let's see how many multiples of 11 are here. And then if you do this, hope you know your 11 times table, you get that. But the remainder is 1. So this is actually 11 times 4792 plus 1. 4792 plus 1. I'm not spending too much for time in the calculations. I work quite rapidly, but you can check this. Sometimes, as you saw, I work rapidly and make errors. Then I'll go back and check. So what's happening? That means we got our ABCD. You see, the number you're looking for is that one there, 47921. Right? When you're dividing 11 times that plus 1 gives you 52713. That's what I got here. 11 times something plus E is 52713. And the way to work out what N and E is to divide by 11. And then you will have your quotient, then becomes your N. That's a quotient when divided by 11. And this is the remainder. It's smaller than 11. So the number you're looking for is 57921. They say find the original number. So that's the answer. See, all very, very interesting. I'm sure you guys are enjoying this because it's all common sense. you know, getting to feel numbers. What are you doing when you are dividing and multiplying and adding natural numbers, and bringing some algebra into it. All that gives you a good sense of where we are going. Okay, so the next problem. A positive integer n has the property that when the last digit is transferred to the front of the number, again, you got a similar problem. The new number so formed is 5 times the old. All right, a positive integer n has the property when the last digit is transferred to the front of the number, the new number is 5 times the old. Okay, now that's quite a mouthful. Now we don't know how many digits this number has got. They don't tell you it's a 5-digit number or 7. Okay, so I'm going to use the symbol n again. I'm going to use the symbol n for this number. Actually, what I want to say is, I'm going to, you see, just as we saw now, we saw that 52795 or something like that is equal to 10 times this plus 5. So if you've got some big number, you could have had this number is 10 times that plus 6. Because it is just that number with 0 at the end added to 6. So I'm going to write this number, although we don't know how many digits it's got, but we can say let 10n plus m be the number we seek. Sorry, this writing is terrible. So we are saying let that be the number we seek. Okay, so what does this mean? That means if I write this thing down like this, it'll be like this n, even e, but you've got, this is the last digit. And this one here has got several digits in it. We don't know how many digits it's got. But let's see, maybe we should give a name to how many digits it's got altogether, because that's quite important. Or maybe we can say n has got k digits, say. Let n have k digits. Because we don't know whether it's a 5-digit number or a 10-digit number. So that's an unknown as well. So what do you have? You have the original number. When the large digit is transferred to the front of the number, then the new number is 5 times the old. So your original number is 10n plus e, and 5 times that is this number here. Where the last digit is transferred to the front of the number. See? So it's something like this: 2, 1, 3, 4, 2, 3, 1, 5, 6, and then you got 6. Put that in the front, and you got 6, 2, 1, 3, 4, 5, 6. No, it's transferred. It's transferred. So you put 6, 2, 1, 3, 4, 5. Right? Then we are told that this new number is 5 times the old. So this thing here is equal to 5 times this. Of course, it isn't. because we just took a random number. Now we are looking for this number here. So this number that we are looking for, this part here is your N. And your E is this. Right? So now what have I got? I've got E here. The E is in front. And your number is here. And how do we write this one now? You got E with the number of zeros. And you got N. This is your N. All right, we said let N have K digits. So this thing here has got K digits. So the K is zeros. So what is this? This is actually 10 to the power of K times E, because you got K zeros. We are saying N has got K digits, plus N. See, when you put that E in the front, you got 10 to the power of K times E. You don't know how many digits there are. And then you're adding N to it, and that is, you'll get this number here. So now you got this equation with two unknowns. Right. And that's the hard part. Right. I hope you understand how this thing works now. You see, when you have these digits and transferring and all that, you must give names, but just be careful. You give names to this thing here. Remember, M is the digit here because this is your digits place, and this is 10 times your previous number, which may have any number of digits. And then we said, suppose it's got K digits, and then you have this story here. All right, so how do we solve this problem? The way to solve this problem is bring all the N's to one side. You got 50N minus N. It's 49N. 5 times 10N is 50N. I'm bringing the N to the other side. Just leave this side intact. You got 10 to the power of K, E, and here you have minus 5E. You bring it to the other side. So you have a nice equation, 49N equals E to the power of 10K minus 5. Okay, because I brought that 10 to the power of KE still on the same side, but I brought the 5E on the left-hand side, I brought it to this side, and that's how you got minus 5E. Because if you brought it to the other side, must be. Okay.
I can't read his handwriting because he's mouse writing.
Thomas, can you please switch off your mic? Okay, now this one here is interesting because E is a digit, you see. E is a digit. Now, a digit times this is a multiple of 49. So the only way you can have this is you could have that E is equal to 7 because this is a multiple of E. E is 49 is a factor of this product. So E could be 7. The only digit which will work is E equals 7. Or you could have E equals 1. Okay, you could have E equal 1. And in that case, you got, if E is equal to 7, then you'll have 7N equals 10 to the power of K minus 5. Or if E equals 1, then you got 49N equals 10 to the K minus 5. I'm explaining the fact that E is a digit, and E is also a factor of the sum. See? E is a factor of the left-hand side, so E is a factor of the right-hand side. So it's a digit. So you could have that E is equal to 7. Right. So now you want this quantity here to be a multiple of 7. And they say, what's the smallest value of N? So I'm going to try out different values of K. Right. I got 7n is equal to 10 to the power of K minus 5. I can't wipe this thing out because I made a mistake. Now you can try different values of K. Now K, remember, is the number of digits of n. So you could have had K equal to 1. Doesn't work. Because you'll have 10 minus 5. And that's not a multiple. This is on the left-hand side, you're going to multiply of 7. Remember, we're working with all integers. So K equals 1 doesn't work. Cross. K equals 2. You have 100 minus 5, which is 95. That's not a multiple of 7. K equals 3. You got 1,000 minus 5. That's 995. And you try to see whether it's a multiple of 7. Divide by 7, you get a remainder. Doesn't work. K equal to 4. Then you got 10,000 minus 5. And even that doesn't work. Right? K equal to 5. Now you got 100,000. 4 nines. Yes, this is a multiple of 7. I'm doing this thing quickly mentally. This is 7 times 14285. Right. So the first value of K, that's the smallest value. All these don't work. We're trying to look for it as small as possible. First value for K, which works, is K equal to 5. So then, what does all this mean? So so this thing here, your 7n is 7 times 14285. 7n is 7 times 14285, right? As we just saw now. And that means that n is 14285. So we've just tried different values of K. K is a number of digits. Okay, so the number that we're looking for, the smallest value of n is 14285, but then your E was 7 in this case. So that's the number. So let's just check this thing here. You can check. We said when you take the last digit and put it in the front, you'll get 714285. But you take the last digit, and if you multiply this by 5, bingo, you'll have this exactly. It works. Or multiply by 5. They said the new number is 5 times the old. This is old. This is a new number. Okay, so this is the answer. I want you to notice something. This number here is a very interesting number. Now, I hope you follow this. It's a little bit tricky, but the idea is to get this equation, somehow get this equation, and then bring the ends to one side as we have always done. You got this. Oh, by the way, you still have the other possibility. You'll have to try different values of K to see so that this becomes a multiple of 49. Right. Now you can see we took nearly 5 steps to get to a multiple of 7. And to get a multiple of 49, you probably have to go very, very much more. So this one here will give you larger values of K. And this will give you K to be greater than whatever we calculated. because the small values of k will just barely give you a multiple of 7 when k is equal to 5 or something, we said. But to get it to be a multiple of 49, you still have to go further down the ladder, which will make the numbers even bigger. So the smallest value of n is what we just got. Okay, I was saying that this is an interesting number because it's the decimal expansion for 1/7. It's a recurring decimal. All right, 1/7. It's the percentages of this are that, you see. So this is an interesting number. And the other interesting thing about this is that I find that this 5 is just one example because if you take so it's a very curious number, and one can see why it works. I've investigated this thing some time ago to find out why it works. Why what works? This. That if you take the different things, 14287, and put 1 at the end, or 12857, or put cut it off from here, you'll get 285714. Or you can cut it off from here with 857142. Or you can cut it from here, you'll have 571428. And if you cut it from here, you have 71428, which we just saw. Right? The interesting thing is this is that if n is this one here is 3n, and this is 2n, and this is 6n, and this is 4n, and this is the one that we're looking at, 5n. Remember the 7 came to the front. So all of these are multiples. If you just twist them around, they're all multiples of the original one. See, it's a very interesting, very curious number. All right, you can go and think about that and just enjoy working with it to see why it actually works. All right, now we're going to go on to the next problem. And the next problem is your assignment problem. How many integer solutions are there for the equation? This. Okay. In other words, you want x and y to be integers. Could be negative, but integers, or 0. Up to now, we only talk about positive integers. But if you say integer, it could be negative, 0, or a positive integer. So this is your assignment problem. And it's got a lot to do with, I'll just give you a hint. You check endings of square numbers. Right. You look at the endings of square numbers, that find out what the endings are. I think I mentioned this at some time. And then you'll see that you cannot get this thing here to be a square. So this thing will never end in what you want it to be. So that's a major hint that I'm giving you. Those who didn't attend this class, they missed out on that hint, but maybe you can tell them if they are in your class, in your school. Okay, number 8. If you write the integers 2, 3, 4, 6, 8 in every possible order to form 5-digit numbers, how many of these numbers will be divisible by 11? This is quite an interesting problem. So you write it in, okay, you can write it as 2, 3, 4, 6, 8. That's one way. Or you can try 2, 3, 4, 8, 6. Or you can try 2, 3, 8, 4, 6. Or you can try 2, 3, 8, 6, 4. Like that. In fact, you've got 120 possibilities, believe it or not. Now, you're not going to go through those 120 possibilities and then divide by 11 to see whether 11 goes exactly into it. And even to write down 120 possibilities, you make sure you're not missing out anything. And then you have to divide it by 11 till the cows come home. And by the time you do all that, you will die of old age. So we have to think of some nice trick to solve this problem. But divisibility by 11 is interesting, see? Because when you got a number which is divisible by 11, 5 digits, is a multiple of 11, what does this mean? So there is a rule for this. Multiple of 11. And this is the rule. It's when you add the alternate numbers, A plus C plus E, and the other set of alternate numbers is B plus D. And if you subtract these, the difference between the sums of the two alternate numbers, this has to be a multiple of 11. Right, so now we have to see if you take 2 of those and you add them, and you take 3 of the others, add them, subtract it, and see if it's a multiple of 11. So that doesn't take too long to try, because let's take them 2 at a time. If you take 2 at a time, you got 2, 3, you got 2, 4, 2, 6, 2, 8, and then you have 3, 4, 3, 6, 3, 8, and then you have 4, 6, 4, 8, you got 6, 8. There are quite a few. Now these are your B, and D. Right, so now in this case here, if you got 2, 3, what are the remaining numbers? You got 2, 3, 4, 6, 8. So you got 4, 6, 8. Oh, it's easier. If you add up all the numbers, what do you get? 9, 15, 23, 14, 18, 20. Right, if you add up all the numbers, you get 23. So this one will give you 5 plus 18, right? The other group is 4, 6, 8. That's how you get 18 here, right? The other group, if I take out 2 and 4, get 3, 6, 8. I don't even have to write it down because 2 plus 4 is 6. So you got 6. Oh, no, actually, you're subtracting. You're subtracting. It's 18 minus 5. That's not a multiple of 7, 11. Okay, but we'll just hold on with that. And here, with 2, 4, sorry, it's 6. 23 minus 6. So you 23 minus 6. Why am I doing this? I got 17 and 6. Oh, 17 and 6 actually works. Because you want 17 minus 6. Where did I get 17 from? I wrote down 2, 4, and I got the other 3, and you add them, that's 17, and you add them, and you got 6, subtract them, and you want to see whether this is a multiple of 11. So this certainly does the trick. Right? And I think none of these, yeah, you got 8 and 15, you got 10, 13, and you got 7 and 16, 9 and 14, and the 11 and 12, 10 and 13, 6 and something. Right. I'm doing it very, very fast. I'm just checking to see what the difference between these sums are. It works only in that. So which numbers have this property? How many of these numbers will be divisible by 11? So let's just remove these things. And I'm going to write down the 5-digit number, but I'm going to put a block. We saw that the twos, these here become 2 or 4. The 2 plus 4 is coming from here. So you could have had 2, 4 like that, or you could have had 4, 2. Right. Now, the remaining numbers are 3, 6, 8. Now you can put 3, 6, 8 here. It adds up to 17, but you can take any combination of 3, 6, 8. Right? The sum will still be 17, and this one here will still be 6, and 17 minus 6 is 11. So you can take any combination involving 6 and 8, 3, 6, and 8, and with 2, 4. So you'll have, I'll actually write them down. I could put 3, 6, 8, 3, 2, 6, 4, 8, for instance. Or that's your 3, 6, 8. Or you could put 3, 8, 6. You could put 6, 3, 8, 6, 8, 3, 8, 8, 3, 6, and 8, 6, 3. So there are 6 ways in which you can arrange those 3 numbers. In this case here, so that case there gives you six numbers. And for this one here, these will give you new numbers though, because you got 4, 2 here. That'll give you, for example, is exactly the same reason. You'll have another 6 numbers. So you'll have 6 numbers there and 6 numbers here. And you get 12 numbers altogether. See? Like for instance, if I took 8, 6, 3, if I got 8, 4, 6, 2, 3, and if I divide by 11, I'm going to see it goes exactly, because 8 plus 6 is 14, 14 plus 3 is 17, 17 minus 6 is 11, so the whole number is 11. So any one of these will do the trick, okay? So you got 6 numbers in that lot, and 6 numbers in this lot, which gives you 12 numbers altogether. So how many of these numbers? The answer is 12. Okay, so let me just go to the next one. Okay, some numbers, oh, you got a long string of, sure, there's a shorter way of writing this. When divided by 7, leave a remainder of 6. So you want n, oh. So let's call those numbers n. So when you divide by 7, you get a quotient, you get a remainder, and the link here is 7q plus, the remainder is 6. So n is equal to 7q plus 6. Okay, that's a quotient. Or it's another quotient. If you divide by 6 now, you divide by 6, you're going to get 6 times the quotient plus 5. Or it's 5 times the quotient plus 4, 3 times the quotient. We don't know what these quotients are, so I'm using Q1, Q2, Q3, Q4, plus 2, and you have 2 plus a quotient, plus 1, right. Now the same number can be written in so many different ways. So I've translated this thing into equations. I've got 5 equations, and there are 5 unknowns, which makes life very complicated. But observe that in each of these cases, if I add 1, n plus 1 is a multiple. Because 7q1 plus 6 plus 1 is 7q1 plus 7. And that's a multiple of 7. I can take out 7 as a common factor. And these are all integers, quotient. When you divide, all these are integers. So it now becomes a multiple of 7 because it's 7 times something. So when I'm adding 1 to both sides, it's a multiple of 7. Likewise, this thing here says it's a multiple of 6 also. Where we have 6q plus 6. If you add 1, you get 5q plus 5, 3q plus 3, 2q plus 2. Right. So in other words, the number you're looking for is a multiple of 7, 6, 5, 3, and 2. Well, if you add 1 to it, n plus 1. Right. So in other words, it's a common multiple. N plus 1 is a common multiple. It's a multiple of a lot of numbers. It's a common multiple. I'll write it backwards. 2, 3, 5, 6, and 7. And you are looking for the smallest. So you're looking for the lowest common multiple, you see? The smallest is the lowest. So the lowest common multiple of these numbers here. So when you try this thing out, you look for the lowest common multiple. I think you get 210. 210. It looks like 210 because 7, 6, 5, 3, 2. Yeah, even 3. I think it's 210. So n plus 1 is 210. Now you have a way of finding the lowest common multiple. I think you did that in primary school. But I can try it out mentally. So that's n plus 1. So therefore, n is 209. Right? So when we say find the smallest such number, you tried out numbers like 45, 46, 47, and so on, and then divide by 7 and work out the remainder and see. You'll see you failed in every one of them until you come to 209, and then you see, oh God, 209, you divide by 7, it leaves the remainder of 6, and divide by 6, you leave the remainder of 5, and so on. And you get very happy because you finally reach the number, but it takes a long time if you do it by trial and error. But this method here, it's a nice, very good application of LCM, see? But just translating it, you write these equations, and then observe that if you add 1 to n, you're going to get a multiple of every one of these things. So in other words, you've got a common multiple. So this interrogates the meaning of common multiple and the lowest common multiple. See, when you did this in primary school, you just had an algorithm to find the LCM, even if you didn't know what LCM means, but you were able to find the LCM of all these numbers, and you had a method, LCM. Find the LCM of 42, 60, and 76. And then you had a way of doing it. 42 equals factorize 60, factorize. Right? You got a recipe. And then you just wrote down what the LCM is, even if you didn't know what LCM meant. Right? But what LCM means is it's a common multiple. It's a multiple of every one of them, but it's the lowest. There's no number smaller than that number, which is a multiple. Okay, so that's a very important meaning of LCM. Okay. Similarly, you have HCF, highest common factor. The HCF is a common factor. In other words, it's a factor of all the numbers which is given, and it all, so it becomes a common factor. And then you say there's nothing higher than that, nothing larger than that, which is still a common factor. So it becomes the highest common factor. Okay, so that's HCF. Okay, now we want to get on to this. And this is the last one, and we're exactly at 6:30. So okay, now this one here is a pretty tricky problem, if I remember correctly. A mathematics competition consists of 30 multiple choice questions. 4 marks are awarded for a correct answer, -1 for the wrong answer, and 0 for a blank answer. What is the minimal number of participants needed to be sure that 2 of them will have the same score? The 2 of them will have the same score in the competition. Now, this is very tricky. So what you've got is, let me try to understand this. You've got questions 1, 2, 3, all the way up to 30. They are multiple choice, and 4 marks are awarded for the correct answer. So if your answer is correct, you get 4. And you've got the wrong answer, -1. And for a blank answer, you get 0. Now this is a nice thing. Sometimes people, multiple choice, they guess, which is not fair, because you can get the right guess without knowing how to get the answer. But now, when you say, if you guessed and you got the wrong answer, you're going to lose marks. So all your positives will, be reduced. So this discourages you from actually writing an answer which you're just guessing wildly. So you rather leave it as a blank. Okay, but whatever it is, then you total all the marks. And so on. Right. You total all the marks and you get an answer. Now, the question is now, what is the minimal number of participants needed to be sure the 2 of them will have the same score? And the score is the sum of all these things. You add up all these numbers. Okay, so now it all depends on how many wrongs you had. So suppose you've got number of wrongs. Let's go correct ones first. Number of correct. Is C. Number of incorrect answers is I for incorrect, and then number of blanks. You can call it B. Right? You got 30 multiple choice questions. You got C plus I plus B. It's 30. 4 marks are awarded for the correct answer. So this will be 4C. -1 for the wrong answer. So for each incorrect answer, you get -1. So altogether, you got I incorrect answers, minus I. And B, you get 0. So it doesn't Doesn't help. No, not equals 30. This is, sorry, this is marks, total marks. You have 4C minus I. All right. Now you want the two people to have the same score, which means that you want to take all the possibilities with different scores. So the question is, how many different scores are there? How many different scores are there? So you take all the possibilities. Like for instance, now we can work out the lowest possible score is where extremely unfortunate case where this guy guesses 30 times and hopes he eats a jackpot somewhere, but the gods were ruling against him, and he got a whole lot of those guesses wrong. Multiple choice. So there'll be 30 negative ones. And the highest, lowest is minus 30. And the highest score so you've got one bright guy who got all right. So he gets 120. Now, for one thing, so the scores can range from minus 30, minus 29, minus 28, all the way. Excuse me, I forgot that I'm talking to you and I'm busy eating nuts here. I'm going all the way to 116, 117, 118, 119, 120. It's possible to have all these scores, which gives you 151 scores actually, where there's a zero amongst them. You have 30 negatives, 120 positives going all the way for, and zero also. So you could have had 151 possible scores. And if you want, what is the minimal number of participants needed to be sure that two of them will have the same score? So if you had 152 participants, two same guaranteed. So there's an example where if you had 152 participants, then you can exhaust the whole lot of the 151 squares, but the next score will have to be one of them, in which case both of them will have the same score. Right. But the question is, what is the minimal number? So the problem is that there may be some numbers here which cannot be attained. Although we are saying all this is possible, but with this scenario, it's quite possible that you don't have. I'm going to clear all these drawings. Okay, so like for instance, is it possible to get the score 1? Let's see, you can put correct, incorrect, and what was this? B for blank. Yeah, B for blank. Can you get these? Now remember, we had 4C minus I. That's the score. So you can't get, for instance, C equals 2, because you've got a multiples of 4. Oh, yeah, I can. I mean, it is possible. If you start from minus 30, these are all negative ones. One of them could be a 0. You decided not to answer the question, in which case you have minus 29, or you could have 2 zeros. So all these numbers are attainable. Minus 30, minus 29, all the way up to minus 1. They're all attainable, because you just put all negative ones at the starting point, and then say, all right, you've got 1 blank, or 2 blanks, or 3 blanks, or 30 blanks, which will give you 0. 30 blanks will give you 0. So even 0 is attainable. The guy didn't answer a single question because he went off to sleep at the beginning of the test. And then, now when it comes to 1, can you get 1? Well, yeah, you could have 1. You could have had 4, -1, -1, -1, and all zeros. So 1 is attainable. So like this, now you can try all these things, but you will see there are some numbers, like for instance, take 119. 120 is attainable, but is 119 attainable? Well, you can get 4 times 29 is 116, right? And you got only one more left because the 29 people have scored that. And 116 minus 1 is 115 you can get, but you can't get, the next one could be a 0 or a -1, and so you can't get 119. You may try 28. That's 112, so you need 7 more. You see, B plus C plus I, we should really do some mathematics here instead of guessing around. This is 30. And you also have, yeah. So if you got 28 people here, then you got only 2 more left. What scores can they get? So you got 112, and they can get 2 -1s or 2 zeros. So like this, at the high level, you can see there are some numbers which cannot be attained. Like with this, you can have -1, -1, or you could have 0, 0, or you could have -1, 0. In which case you got 112, 110, 112, exactly. 112 minus 1 is 111. So you can get that, but you try 109, I think 109 probably doesn't work. Because 109 is not here. You can get 427s, which is 108. And you have 3 more. Can the 3 add up to 1? No way. You only have -1 zeros. Oh yes, you can have. Yeah, no, you can't. You can't have it adding up to 1. With only zeros and -1s inside here. I don't think so. So this is not attainable. So I'll just give you an example of one which is not attainable. Now the thing is you have to try out which numbers are not attainable and eliminate that from the 151. And I think you see that 6 numbers are not, if I remember correctly, you can try this thing out. I think the answer is 145. Mm, yeah. You just hold on a little bit because I've got all the solutions. Um, oh, I'm sorry. This is one of those things I'm not very good at. Never tried opening up more than one window. Oh, there we go. There we go. So we're going to go to question session 7. You see, I have all the solutions, which I don't share with anybody. One day with those people are marking. So you got many of these things I've already done now. I've finished session 1 up to session 6. And we are doing session 7 now. Yeah, so this is what we've been doing. You see all this? 2, 4, and all that. We did all this. And this is the one here. You see how many scores are possible? Then I said the lowest possible score is this. Are all 151 scores attainable? Clearly, these are attainable. I went through all this. But now, oh yes, 4m plus 1 equals 4 into m plus 1 plus 3 times minus 1 is attainable. Oh, I've got some fancy thing here. So a multiple of 4 plus 1, is that attainable? Well, you got a multiple of 4 and you got a multiple of -1, right? And you can do this. You can have 4m plus 1 minus 3. So 4m plus 4 minus 3 gives, so this is attainable, but provided that m plus 1 must be less, m plus 1, this is the number of people, plus 3 must be less than or equal to 30. So this is good mathematics here. So provided the number of people, m plus 1 plus 3 is less than or equal to 30, because it's less than or equal to some of them I have got 0 this. So this means that m must be less than or equal to 26. So as long as m is less than or equal to 26, it's attainable, right? And you go up to this. 109, we saw that this was not attainable. When you put m equals 27, you get this. But for m equals 28, also, m equals 29 is not attainable because m must be smaller than or equal to 26. So understand, you're looking to see whether a number of this form, in other words, 1 more than a multiple of 4, is it attainable, right? And then we write it like this, which is a very nice, neat trick here. Because you can get, these are the correct ones, and these are the incorrect ones, and the zeros are not counted. So you can get this. The number of people is m plus 1 times plus 3, where the scores are 4 and -1. So but you need to have the number of contestants must be less than or equal to 30. And that gives you a bound for 26. So the same thing for 4m plus 2, and you do something like that, and there you see that m will have to be less than or equal to 27. Right? So for 28 and 29, it doesn't work. See? So when you put m equal to 28, 28 times 4 is 112 plus 2 is 114. That's it. And m equal to 29, 118 is not available. So you got these three, those three, see? And there's one more. I told you 145. So you have 6 numbers which are not attainable using this logic. See, I forgot that this very neat way of doing this. You ask yourself, is 4m attainable? Yes, because you'll need to have 4 correct ones. M correct ones and all zeros. It's always attainable. But what about 4m plus 1? If you're dividing by 4, the remainder is either 1, 2, or 3. So there are only 4 possibilities. A multiple of 4, multiple of 4 plus 1, a multiple of 4 plus 2, a multiple of 4 plus 3. So try multiple of 4 plus 1. Is that attainable? Yes, it is attainable for everything except for 3 of them. And there you use the fact that the total number of questions is 30, right? So the total number of, these are the number of questions, m plus 1, correct ones, incorrect ones, and so on. And that way you can find out which numbers are not attainable. Okay, I took 20 minutes more than what I normally do, and I'm happy to see that the 6 participants are still here. But this was a rather tricky answer. So 145. So these are attainable. So to get the minimum number is 146, not 152 as we saw earlier on. Right? We saw at 152 it'll work. But what is the smallest? The smallest is 146. It's a hard question. Huh? But some of you are very bright. So I have no doubt that some of you would have sort of logically decided. You might not have done this mathematics like this, but you could have eliminated those numbers by trial and error and come to the answer 145 without having to have a proper mathematical background like the way I have done to explain that these are the only answers. Okay, guys, thank you very much for listening. I can talk to you if you want. Let me just share. All right, you can put down anything that you want to say in chat, and I'll be quite prepared to answer in chat, because I think all of you, your mics have been switched off for good reason. Sometimes people want to talk. Okay, so you don't have anything to say because there's nothing in the chat column. So with that, I wish you a good night. Okay. Enjoy the rest of the evening. Bye.